In section 4.8, we're going to talk about this thing called L'Hopital's rule. And yes, that's how you pronounce this. I know it's kind of weird looking with the apostrophes and stuff. But per some French guy that I knew in grad school, apparently the way you say this is L'Hopital. L'Hopital's rule. Anyways, what L'Hopital's rule does is it allows us to evaluate some of the limits that we saw in the previous section in a much nicer way. L'Hopital's rule is pretty great. So for example, maybe you remember in the previous section I gave you this limit. The limit as x approaches infinity of x to the fifth power divided by e to the x plus 14. And this is kind of a strange limit to evaluate because as x gets really large, the top of this fraction gets really large, but the bottom of this fraction also gets really large because e to the x gets really large. We know what happens, loosely speaking, when we have a constant divided by something that gets really large, and we know what happens, again, loosely speaking, when we have a number that gets really large divided by some constant. But in this case, the top and the bottom are getting arbitrarily large. This limit that you see here is kind of this infinity over infinity type. And unlike these two types, we can't immediately evaluate limits of this type. It's what's called indeterminate, a word that we'll learn a lot more about as this section goes on. Anyways, the way I got around this is I said, well, just trust me, exponentials always beat powers. In other words, this e to the x gets large a lot quicker than this x to the fifth power does. So even though the top and the bottom of this fraction both eventually approach infinity, the bottom, loosely speaking, gets there a lot quicker. So this kind of acts like the case where we have a number divided by infinity. The bottom infinity beats the top infinity if you want. And just like in this case where we have a constant divided by a number that gets arbitrarily large, we see that the value of that fraction approaches 0. Hence, the limit as x approaches infinity of x to the fifth divided by e to the x plus 14 is equal to 0. And that's entirely true, but this reasoning of exponentials always beat powers is a pretty weak justification. And while it works on this problem, you might wonder about other ties. Like for example, if I asked you the limit as x approaches 0 of sine of x divided by x cubed. Well, when the x-coordinate gets really, really close to 0, because the sine of 0 equals 0, the top of this fraction is going to approach 0. Similarly, when x gets really close to 0, x cubed is going to get really close to 0. Unlike this infinity over infinity indeterminate form, down here we have this 0 over 0 indeterminate form. We know what happens when we have something that approaches 0 divided by some non-zero constant, and we know what happens when we have some non-zero constant divided by something that approaches 0. These two forms were okay in our previous section, but this 0 over 0 form was not. How do you evaluate this limit? Well, really what it's going to come down to is kind of similar logic for how we evaluated this limit up here, where we kind of thought about which thing beats the other thing, loosely speaking. Up here, the bottom approaches infinity faster than the top approaches infinity. So you're kind of thinking about a fraction where the bottom is bigger than the top. When the bottom of a fraction gets really large, the value of that fraction approaches 0. The same logic works here. We have to consider what gets close to 0 quicker, the graph of sine of x or the graph of x cubed. And that's not at all obvious. But it turns out this is a problem that L'Hopital's rule can solve really easily. Before I tell you L'Hopital's rule, I feel kind of obligated to give you this quick aside right here. This is something that I didn't know when I first learned L'Hopital's rule, and I found it pretty interesting. So if you're interested, you could pause the video and kind of read this on your own. But the big punchline is, there was this guy named L'Hopital who was really rich. And I mean, I'm sure he was pretty smart too, but he wasn't nearly as brilliant as this guy Bernoulli. There are actually a couple different Bernoullis. The one in particular we're talking about here is Johann, although all of the Bernoullis were kind of brilliant. Anyways, L'Hopital had the money and Bernoulli kind of had the brains, so they worked out this agreement where when Bernoulli came up with these really interesting mathematical facts, he allowed L'Hopital to take credit for them as long as L'Hopital paid for them. And one such fact that probably should be credited to Bernoulli, since he's the one that supposedly came up with it, but instead is credited to L'Hopital, is this thing called L'Hopital's rule. Anyways, what's L'Hopital's rule? What L'Hopital's rule says is when you have an indeterminate form, and we're going to have a lot more on that later, but for now, ignore that fact. Just assume that we have an indeterminate form. When you have an indeterminate form, instead of evaluating that limit, you can evaluate the limit of the quotient of the derivatives. What am I talking about? The limit as x approaches 0 of sine of x divided by x cubed is an indeterminate form. Again, I know that I owe you a better explanation of why it's an indeterminate form, but maybe for now you'll trust me. Because we have an indeterminate form, we can use L'Hopital's rule. This is equal to, and sometimes people put a little h on top of the equal sign to signify that they're using L'Hopital's rule to come up with this equivalence. It's equal to the same limit, the limit as x approaches 0. But instead of looking at sine of x divided by x cubed, we look at the derivative of sine of x, which is cosine of x, divided by the derivative of x cubed, which is 3x squared. The nice thing about this limit in red is it's not an indeterminate form. What do you mean it's not an indeterminate form? Well, in short, because I can determine what the limit is. When the x-coordinate gets really, really close to 0, the cosine of x gets really close to 1, because the cosine of 0 is equal to 1. However, when x gets really close to 0, whether we're slightly greater than 0 or slightly less than 0, 3x squared is going to get really close to 0, but be slightly positive. Because even if x is negative, the squaring part makes it positive. So what I kind of end up with, loosely speaking, is 1 over a positive value of 0. This is non-standard notation to write this 0 with the plus up in the superscript, but I kind of like it because it shows my work for what's going on. As we learned in the previous section, 1 divided by 0, because the denominator is getting arbitrarily small, is going to give us an infinite result. And all we have to do is figure out whether it's positive infinity or negative infinity. Since we have a positive number divided by a positive number, we get positive infinity, which we can just write as infinity. The limit as x approaches 0 of sine of x divided by x cubed turns out to be infinity. Oh, right, and you said sine of x over x cubed was 0 over 0. Does that mean anytime I have a form that's 0 over 0, I get infinity as my answer? Absolutely not. The reason we get infinity as our answer here, very informally speaking, is because x cubed gets close to 0 quicker than sine of x does. So we kind of have this fraction here where the top, yeah, it's kind of small, but not nearly as small as the bottom. And if you think about what happens to a fraction when the bottom of that fraction is really, really small, in your head, maybe you're thinking, I don't know, 1 divided by 0.00001, the value of that fraction gets really, really large. Because x cubed gets close to 0 quicker than sine of x does, the value of this limit ends up being infinity. And if you think about it that way, L'Hopital's rule actually has some intuitive sense to it, because all the derivative is telling us is the rate of change. So sort of the idea is, evaluating this limit, we don't have enough information to figure out what happens when I divide these two things because they're both getting close to 0. So what I have to do is figure out which one gets close to 0 quicker. I have to examine the rates of changes of the top of the fraction and the bottom of the fraction. That's what L'Hopital's rule does. Quick comment here. Don't confuse this with the quotient rule. The quotient rule is something we learned earlier in the class that says if you're taking the derivative of something divided by something, you take the derivative of the top and then you leave the bottom alone, and you subtract from that the derivative of the bottom, leaving the top alone, and you divide that whole thing by the bottom squared. The quotient rule has nothing to do with L'Hopital's rule. We're not taking the derivative of this quotient. We're taking the derivative of the top of the fraction and then separately taking the derivative of the bottom of the fraction, because we want to examine, does the top of the fraction approach the given value, 0 or infinity, quicker than or slower than the bottom of the fraction does. Let me give you one more example of L'Hopital's rule and how it works before I end this video, and I'll save all the minutia, sort of the fine print on what an indeterminate form is, for the next video. The example that I started this video with, the limit as x approaches infinity of x to the 5th divided by e to the x plus 14. I claim that's equal to 0. I gave you the explanation that exponentials always beat powers. I even showed you some graphs in previous videos showing how e to the x gets big quicker than x to the 5th gets big, informally speaking. Well, let me show you how L'Hopital's rule confirms that. If we're trying to evaluate this limit, when x gets arbitrarily large, x to the 5th gets really large, and e to the x gets really large. So I kind of have this infinity over infinity, which will turn out to be one of our indeterminate forms. And therefore, we can use L'Hopital's rule. L'Hopital's rule tells us that this limit is equal to the limit as x approaches infinity. I want to keep that part the exact same, but then I take the derivative of the top and the derivative of the bottom. So 5x to the 4th power is the derivative of the top, and the derivative of the bottom, because it's a sum of terms, is the derivative of each of the terms individually. The derivative of e to the x is just e to the x, and the derivative of this 14 is just 0. So L'Hopital's rule tells me that this limit is equal to this limit. And you're like, okay, cool, and now just evaluate this limit. Well, unfortunately, I can't, because this is still an indeterminate form. Because think about what happens as x gets really large. 5x to the 4th power is going to be really large, and e to the x is going to be really large. I still have this infinity over infinity indeterminate form, so I can use L'Hopital's rule again. Because this is an indeterminate form, the limit as x approaches infinity of 5x to the 4th over e to the x is the exact same as the limit as x approaches infinity of 20x cubed, the derivative of 5x to the 4th, divided by e to the x. And now I can just evaluate this limit, and maybe you can kind of see where this is going. I still can't evaluate this limit. It's still an indeterminate form, because just like x to the 5th and 5x to the 4th, 20x cubed gets arbitrarily large as x gets arbitrarily large. And as we've already talked about, e to the x gets arbitrarily large when x gets arbitrarily large. So I still have this infinity over infinity type, so I can use L'Hopital's rule again. The limit as x approaches infinity of 20x cubed over e to the x would be 60x squared over e to the x. Still an indeterminate form. Use L'Hopital's rule again. The derivative of 60x squared is 120x. And the derivative of e to the x is, again, just e to the x. And try again. Stare at this thing. Is this a form that you can determine the limit of? Nah, it's still infinity over infinity, because when x gets really large, 120x gets really large. So I can use L'Hopital's rule yet again. I get the limit as x approaches infinity of the derivative of 120x, which is just 120, divided by the derivative of e to the x, which is just e to the x. And now be careful. It's tempting to take another derivative and see what happens, but you can't. The reason you can't is because this is not an indeterminate form. This is a constant, the number 120, divided by something that gets arbitrarily large. I still haven't defined indeterminate forms for you, but I've kind of alluded to the fact that infinity over infinity is an indeterminate form, and infinity over infinity is the form that each of these different limits takes on. But this one does not. This is a constant divided by something that gets arbitrarily large. And as we saw in the last section, when you have a constant divided by something that gets arbitrarily large, that limit approaches 0. Think 1 divided by 100 billion is 0.00000. I don't know how many zeros, and then a 1 at the end. Damn near 0 because the bottom is so large and the top is not. Anyways, through this chain of inequalities, we figured out that this original limit that we were trying to figure out is just equal to 0. The same conclusion we came to in the previous section when I told you exponentials always beat powers, and maybe you felt a little bit uncomfortable about that. Now I can justify it.